Okay, good morning, everyone. Hope you're all well. Not too much housekeeping this morning. Hopefully, you are continuing on with deliverable 2, which is due this coming Monday at 11:59 p.m. As always, any questions about the final project? All good so far? Okay, so just a couple of updates to the schedule. Just as a reminder, we're working our way through this theme on open challenges in the field of evolutionary robotics. And we are going to finish our discussion today on the 1, 2, 3, 4, 5 different approaches we're going to consider about trying to cross the reality gap. We're a little bit behind where I wanted to be at this point in the semester. Obviously, this semester is a little unique. So I've grayed out a couple lectures here that we are going to skip over. I will put up the links for those lectures for those that are interested. Evolutionary robotics is fascinating. We can't cover everything in one semester. So we'll finish up lecture 19 today, and then we'll move on directly to addressing ways to scale up evolutionary robotics. Okay, we'll finish up lecture 18 now, which was this idea of transferability. And just to remind you, the intuition for transferability is that we're going to try and evolve controllers that produce desired behavior in simulation, but also have a good chance of transferring to reality if we transfer them. Okay. And in order to do that, the authors of this paper used multi-objective optimization, where we're treating each solution in the population as a point in two-dimensional space, and the coordinates, the x and y coordinates of each solution, represent the values of that solution. So now we don't have a single fitness value anymore, we have multiple fitness values. We delete individuals that are dominated, that are worse in terms of both fitness values or both objectives, and we make randomly modified copies of the survivors on the Pareto front. Okay. So last time we started to look at a typical experiment in the transferability project, where at the beginning, obviously, we don't know what the transferability of any given controller is. So being optimists, we take the one that produces the fastest moving behavior in simulation, which is this behavior, and transfer it to reality. And unfortunately, this solution ended up having low transferability. The physical robot did not do what the simulated robot predicted it would do. Okay, so we now have a horizontal coordinate for this point, low transferability. Which one do we transfer next? Well, we could transfer another one that produces fast motion in simulation, but that one, because it's close or similar to the one we just transferred, is likely to have similar transferability, which in this case is low. So perhaps we go somewhere else in the population to transfer it. So in order to do that, what we're going to do is we're going to try and estimate the transferability of a controller that we've not yet transferred to reality, based on its behavioral similarity to a tested controller. The more similar to the two controllers are, the more likely they're going to have similar transferability. And if one of them has already been transferred, we know what its transferability is, and we can estimate this controller's transferability from it. Okay. Every question in science, every answer in science raises 10 more questions. So that's great that we want to measure the similarity between behaviors generated by controllers. But how do we measure the similarity between behaviors? We could simply just take fitness, which is the distance traveled. But in this case, the investigators actually isolated 3 different features of the behavior produced by a given controller, F1, F2, and F3. And these features capture different aspects of the way in which the robot moves. F1 is the aspect of behavior we're interested in, which is the total distance traveled by the robot. F2 is the mean height of the robot's body during travel, and F3 is the final orientation of the robot's body when it stops moving. Why did they add these additional two features? It's not explained in this paper, but the idea behind this is that just the distance traveled by the robot might not be enough to accurately measure the distance between controllers. We might have two controllers that have very similar F1s. We have two controllers that cause the robot to move about the same distance, having the same F1, but one of them may cause the robot's body to bounce up and down quite a bit as it moves, or maybe actually we're talking about mean height here. So let's assume that one controller causes the robot to crawl on its belly as it moves forward. The other controller causes the robot to stand on its tippy toes and move the same distance. So if they have similar distance, we might predict that they have the same transferability, but something that drags its belly across the ground and something that walks on its tippy toes, you could imagine that that feature is actually more predictive of whether a controller is going to transfer from simulation to reality or not. They don't know which features are more predictive of transferability. Nobody does yet. So in this case, the investigators just threw together three that kind of span different aspects of the way the robot moves. Speed of travel, how it moves, and how it ends up at the end of movement. So that means that for each controller, we can assign to that controller a vector B that has three elements to it, F1, F2, and F3. And then we can define the behavioral distance, B dist, between controller 1 and 2 as the Euclidean distance between these two behavioral vectors. So if we want to ask how similar two controllers are, we run both controllers on the robot. We look at these different aspects of how the robot moves and take the Euclidean distance. So we're going to start to use some notation here where C subscript I corresponds to the ith controller and B sub I is going to correspond to the ith behavior produced by that controller, by the ith controller. Okay, so now we have a way to measure similarity, but how do we define transferability of a controller for a controller that we have not yet transferred a controller that we have transferred to reality? We can now use our behavioral distance function and define the transferability of the ith controller as the negative of the distance between the behavior produced in simulation and the behavior produced in reality by that ith controller. Why the negative sign? If you have an idea, go ahead and type it into chat or feel free to unmute yourself and offer an idea. We're defining the transferability of a controller as the negative of the distance between S and R. What's the negative for? Any ideas? Still a little too early in the morning. So transferability is in essence the inverse or the opposite of behavioral distance between what a controller produces in simulation and reality. So we could have taken 1 over. In this case, they just put a negative sign here. So maximum transferability means the controller produces identical behavior in simulation and reality, which means we're going to have identical behavioral vectors here. So the distance between the behavioral vectors from sim and the behavioral vector from sim and the behavioral vector from reality, the Euclidean distance is going to be 0. So negative 0 is 0. So the highest maximum transferability is 0. And the more these two behaviors diverge, the more negative the transferability metric becomes. So higher values of this are better. Yeah? Okay. Okay, so now that we can define transferability, we now need to define the estimated transferability of a given controller. What happens for it's easy to define transferability for a controller that we've already sent to reality. How do we estimate transferability for a controller that we have not yet sent to reality? The way we do that is we're going to take that controller, the behavior it produces in simulation, and measure its average distance to other controllers that have been transferred to reality and their transferability. So bear with me here. I'm going to start with this term here. So we're going to sum over, we're trying to estimate the transferability of controller C. So we're going to sum over all of the controllers in the set CT, where CT is the set of already transferred controllers. So we're going to assume we've already sent one or more controllers to reality. We're going to take each of those controllers out of CT, one after the other, and we're going to compute the transferability of that controller that we just pulled out of CT. We know exactly what the transferability of that controller is because by definition, we've already sent it to reality. We're going to divide it. So we're basically taking the average transfer. Actually, let's forget this term and this term for a moment. If we imagine this, we're just taking the sum or the average of all of the transferabilities of the controllers sent to reality so far. And that's actually probably a good first order approximation of the transferability of C. If we've sent 17 controllers to reality and on average we get this amount of transferability, that's a good estimate for now of C. But we can actually do better than just taking the average of all transferabilities for the controllers in C sub t. When we compute the transferability of C sub I, we can divide it by the behavioral distance in simulation of the simulated robot controlled by C and the simulated robot controlled by C sub I. We're dividing by this distance. Can anybody see why? So we're now computing a weighted sum where each element in the sum is the transferability of C sub I, and we're weighting it by B behavioral distance. Why? What's the intuition here? If we're computing a weighted average of anything, and some of the elements in that average, if we weight some of them more than others, then those elements count more towards the weighted average, right? They're more important. If the weight is smaller, then we're obvious that the contribution of that element to the weighted sum or the weighted average is less. Anybody see the intuition here? Why are we dividing by B dist? Okay, let's think about the C sub i's that we're pulling out of the bag CT. If we pull out a C sub I that is very close to C, so it's similar, it produces very similar behavior in the robot to C, then we're dividing by a very small number. The distance between C and C sub I is going to be small. So that small difference, we're dividing by a small difference, which magnifies the contribution of the transferability of C sub I to this weighted sum that we're computing. Again, this might be a little bit different from what you've seen before because usually for a weighted sum, we're multiplying by the weight. Here we're dividing by a weight. If the distance between C sub I, if C sub I is very different from C, it causes the simulated robot to move in a very different way, then the denominator here is very large, and it decreases the influence of this value on the weighted sum. So we're trying to estimate C by averaging the transferabilities of all the controllers we've sent to reality, but we're giving more weight to those that are closest to the current controller C that we're trying to estimate. This term up here that we're multiplying by, you'll notice that we're summing over the same things that we're dividing by here. This is a normalization term. So we could rewrite this where we replace the division by a multiply and the multiply by a division, and you'd have a normal weighted sum, a weighted average calculation. So this is a weighted average where we're giving more weight to the controllers that are closer to C. So when we compute all this, we now have an estimated transferability for controllers that we have not yet sent to reality. And I'm going to just back up a little bit here. I showed you this picture before. This is the multi-objective optimization here, where we have each point in the population. We have a population of controllers, all the circles here. The height of the circle is the distance that controller causes the simulated robot to move. And the horizontal axis is this estimated or approximated disparity we just mentioned. We're approximating, or we can estimate transferability on the horizontal axis now. So armed with this estimated transferability, we can now run our multi-objective optimization method. At every generation, we can compute the distance traveled by the simulated robot using each controller. We can estimate the transferability of that controller, and we delete controllers that produce slow-moving simulated robots and controllers that have low estimated transferability. We're going to try and maximize forward travel and maximize estimated transferability. Okay, so which controller do we try in reality next? Now we are armed with enough machinery to be able to answer this question. At the end of every few generations, we can pick however many generations we want. We're going to pick one controller from the population that has not yet been sent to reality and send that controller. What controller do we send? We've run our move for a while. We have our population of controllers. Each controller has two numbers associated with it: how far it causes the simulated robot to move, and our estimate of the transferability for that controller. Which one do we send? What the authors chose to do in this case was to send the controller that's most different from those in the current population. So remember that multi-objective optimization gives us back this Pareto front. We usually don't have a clear winner. There isn't one controller in the population that has higher behavior and higher estimated transferability than all the other controllers in the population. Some have higher estimated transferability, and some cause the simulated robot to move faster. Which one do we send? In this case, they choose to send the one that is most different from controllers that have been sent before. How do we define most different? We can visit each controller in the current evolving population. We can take that controller that we're currently considering, C, and we're going to compare it against every other controller that we've sent to reality so far. And we're looking for the controller in the current evolving population that is furthest from all the controllers we've sent to reality so far. This is an idea that was inspired by the evil starfish that we saw last week, where the evil starfish is always trying to do something new in reality to learn as much as it can about reality. In this case, it's not the robot that's deciding what to do next. It's the evolutionary algorithm deciding what controller to send to reality next. How do we know which controller in the current evolving population is most different? We compare it to each C sub I, and at each point we measure the distance or the difference between C and C sub I using our behavioral distance metric. So we now know how different C is from all the controllers we've sent to reality so far. And we assign the diversity, or you can think of this as the uniqueness of C. We assign it the minimum of all of those distances. We might have a C which is very far from a whole bunch of other C sub i's that we've sent to reality, but there's one C sub I that we've already sent to reality that's actually very close to C. If we take the minimum, that C would have low diversity. We have another C in the population, and it's closer on average to all the other CIs, but all the other CIs, there is no one CI that is very close to C. That particular C would get a higher diversity. It's more unique. Okay, so in this experiment now, what we've finished describing is evolving this population to try and maximize behavior and estimated transferability. At every point in time, we pick one of these controllers that's very unique and send it to reality. Maybe it transfers well, maybe it doesn't. We bring that information back, and that transferred C goes into the set CT of transferred controllers, and we recalculate the estimated transferability of all the points in the population, because now we have an additional C sub I to compare them against. We can make a better estimate of the transferability of the not yet transferred controllers. So you can think that once we send a C and bring it back from reality, the horizontal positions of all of the points here are going to shift a little bit. That might cause us to have to recalculate the Pareto front, continue evolution for a while, maximizing behavior and estimated transferability, pick another unique controller, send it to reality, and back and forth, like in the Evil Starfish project. I showed you what happened when they sent the first random control. They sent the first controller to reality, not a random controller. It was an optimized controller in simulation, which ended up having low transferability. After going back and forth between simulation and reality, they eventually had a controller here that causes the simulated robot to have high behavior, to travel a far distance from the origin, and this particular controller has high estimated transferability. When they transferred this one to reality, it transferred well. The estimated transferability was a good estimate. They managed to cross the reality gap. One interesting thing about this, there's several interesting things about this experiment. One of the things I think is interesting is if you look at these two simulated behaviors, they look, at least to me, they look very, very similar, but one of them fails to cross the gap and one doesn't. I've watched these videos dozens, if not hundreds of times. I can't see what the difference is that might cause one to transfer well and not the other. But this algorithm somehow knows. It knows to estimate the transferability of this controller to be high. And in retrospect, if it went back and estimated the transferability of this one, it would say this one is not likely to transfer well. Just goes to show why the reality gap is so challenging, and so many people have spent so much time trying to figure out clever algorithms to cross it. Okay, any questions about the transferability project before we push on and talk about the final attempt to cross the reality gap that we're going to discuss in this course?
Professor, I have a quick one.
Sure.
With the WEGED design, are the wheels allowed to freely rotate, or can they lock up?
They can in this particular robot that they use, but in this experiment they locked the wheels. So the wheels, it's kind of hard to see in these videos, but the wheels are not being they're not being used here. Actually, this is one of the advantages of working with WEGed robots. If the robot or the investigator knows that the robot's going to be moving over flat, relatively horizontal surfaces, actually, sorry, the other way around. When it's moving on flat horizontal surfaces, you should unlock the wheels. But if the robot senses that it's moving over very rough, uneven terrain, the robot can lock up its wheels and act like a legged robot. So by locking and unlocking the wheels, it can sort of dynamically shift from being a wheeled to a WEGed to a legged robot and back again.
Okay, thank you.
Yep, you're welcome. Any other questions before we push on? Okay, so we've been looking at approaches to solve this problem in chronological order, starting from about the mid-90s. And the last one we're going to look at, robots that adapt like animals, this was actually reported only a few years ago in 2015. So we're moving up to basically the state of the art now in trying to cross the reality gap. This work was carried out by the same authors that the same authors that worked on the Transferability project. So there, you're going to see some overlap from that project into this one. These are also colleagues of mine, and they also adapted some of the ideas from the Evil Starfish project into what they call the intelligent trial and error, or what I'm going to call today IT&E for short. And what they borrowed from the Evil Starfish is they're going to use their method not only to cross the reality gap, but also to allow the robot to recover from lost limbs. And my colleagues are big dog people. Some of you've probably seen videos like this before. This is a three-legged dog. Perfectly healthy, perfectly happy, and perfectly mobile. A lot of three-legged dogs can run just about as fast as a four-legged dog. Doesn't seem to slow them down. Doesn't seem to slow them down very much. Okay, so like the Evil Starfish, they're going to try and cross the gap and allow the robot to recover from unexpected injuries. In this experiment, they're going to be working with the Hexapetal robot that you see here. In each leg, there are 1, 2, 3 servo motors, which means that each leg can rotate up and down, forward and back, and also, and the third one is in the knee or the elbow. So we've got a total of 3, 6, 9, 12, 15, 18 total motors, 18 total degrees of freedom. So a pretty complex robot here. Okay, and they're going to break off some legs and see if the robot can recover. The goal of this project is similar to the Evil Starfish project, but the main goal here is they want the robot to recover as quickly as possible. In the Starfish project, I showed you that the Starfish performs 16 exploratory actions, then becomes damaged and performs another 16 actions. Those 32 actions alternating with updating the simulator and the understanding of self takes a long time. In a lot of robotics applications, if something suddenly goes wrong, you want the robot to be able to recover in 1 or a few or at most 3 trials. For example, if we're working with a robot if we're working with a planetary rover and it's on a surface like the surface of a crater and it is sliding down the surface of the crater and it is accelerating, it is starting to fall, and that is not something that the robot expected to happen. You want the robot to be able to figure out what the problem is and recover very quickly. A rover that crashes into the surface of another planet and loses part of a leg, but it's on a flat plateau and it's relatively safe for the time being. It's got all the time in the world to think and dream up a way to recover. That's not always the case. So this algorithm is designed for rapid adaptation to damage or injury or finding yourself in a dangerous situation. Okay, so here's the little cartoon of what we're going to see the physical robot do. They're going to break off half of one of the 6 legs, and the robot is not going to move straight. It's going to turn to the left and travel relatively slowly. That's its first exploratory trial. On its second exploratory trial, it's going to actually move a little bit more straight and a little bit faster. So it's already going to start recovering by the second trial. And by the third trial, in many cases, as we'll see, it's back to traveling almost as fast as it did without the loss of the leg. Okay. How are they going to do this? The way they're going to do this is to produce a prepared robot. What do I mean by prepared? This robot is going to perform millions of simulations before before the physical robot is ever deployed into its task environment. It's going to come armed with not just plan B in case something goes wrong, but it's going to come armed with plan C, D, E, F, G, 20 million contingency plans. When something happens, it's going to efficiently look through this set of several million contingency plans to find the one that allows it to recover quickly. Sounds like a bit of a magic trick. How is the damaged robot going to search through 20 million compensating behaviors that it found in simulation to find, with just 3 attempts, a one that recovers function? That's the heart of this algorithm, is how to actually do this efficient search well. Okay, so I'm going to show you this video, which is what the robot does before it's deployed into the world. It's going to use a particular type of evolutionary algorithm, which we'll talk about in a little bit. This algorithm is searching for ways that gets the simulated quadruped to move, but this algorithm is going to explicitly look for diverse controllers that produce different ways of moving. In this case, they found a controller that causes the left middle leg, sorry, I'll back up a little bit, that causes the left middle leg to spend less than 10% of the time on the ground. Same evolutionary algorithm produces another fast-moving gait, but in this case, it's the front left leg that spends relatively little time on the ground. Same evolutionary algorithm, they found another controller that also causes the robot to move quickly, but now the front 2 legs spend little time on the ground, so large flight phases for the 2 front legs. Same evolutionary algorithm, yet another diverse way of moving. In this case, 3 legs spend most of the time off the ground. So up till now, we've been looking at populations of controllers where we're looking for kind of one controller that causes the robot to move quickly, or one controller that transfers well to reality. In this case, they want as a diverse portfolio of good controllers. The nice thing about working with a hexapod rather than a quadruped is there are many, many different ways to move. We talked about perverse instantiation. Here's a great example of perverse instantiation. The robot travels forward, which is exactly what we want it to do, but perhaps not in the way we wanted it to. Okay, so the robot now has a very large number of contingency plans. And as I mentioned, it's going to try and search through those contingency plans quickly and efficiently to find ones that recover from damage. I might skip around the second video. I want you to focus in this video on the physical robot now. Here's the robot. Let's just focus on this one for a moment. In its undamaged state. So they already have a controller that they transferred from simulation to reality that works well for the undamaged robot. Oh, sorry. So here's some of the gates that we just saw, and they're going to embed all these diverse controllers into a data structure, which is this colorful plot you're going to see in a moment. You can imagine this as a whole bunch of different bins, and they're going to put these diverse controllers in different bins, and they're going to keep all those bins, all those solutions open. Okay. So here goes the undamaged hexapod. Travels 2.5 meters per second, pretty fast. One of the legs loses power, and that controller that worked before no longer works. They're going to reach into this set of bins, this evolutionary algorithm that they've already run, where they've got lots of different kinds of controllers. Lots of different kinds of controllers that worked well for the simulated robot. I'm going to just pause this for a moment. The idea here is we're going to try and rapidly recover from damage, but there's always a cost for an advantage, which in this case is rapid adaptation. The cost is that among this diverse set of controllers that work well for the simulated hexapod, they all work well for the simulated undamaged hexapod. So if the hexapod becomes damaged, the assumption here, and it's a bit of a risky assumption, which is that there's going to be some controller among all these diverse controllers that worked well for the simulated hexapod and also works well for the physical damaged hexapod. You'll notice when we watch the videos of all the controllers, some of them lifted 1 or 2 or even 3 legs off the ground. You can imagine that some of those might be useful if you lose a leg. If you lose your front left leg, and there's a controller that for the undamaged hexapod that did not use the front left leg, then you're probably in good shape. Alex says, does the robot know which leg is damaged, or is it figuring out a new movement pattern based on behavior alone? The answer is the latter. This robot does not know. It does not know, like the evil starfish, it does not know what's gone wrong. All it knows is that now it's traveling much slower than it did before. Traveled 0.25 meters per second before. Now it's traveling 0.03 meters. Now it's traveling 0.03 meters. That's the only information that it has to go back in and find a new controller. Actually, not a new controller, to pull out an existing controller that undoes this slowing down. And I'm going to talk about how it does this efficient search in a moment. But for now, let's just focus on the result of this algorithm, how it helps the robot. We'll talk about the technical details in a moment. Okay, here's the robot's first attempt to recover. It went from 0.03 to 0.13, so it's already doing a little bit better. But still not great. Here's its second attempt, still not great, 0.1. It actually did a little worse. Third attempt, 0.17. It's adapting a little bit. Fourth attempt, 0.2, almost back to 0.25. Fifth attempt, 0.24, it's recovered. So with 5 attempts in this case, the damaged robot is traveling. Here's a 6th one that doesn't work very well. It's going to discard this and go back to the 0.24 that we just saw. So after 6 attempts, it goes back to the 5th attempt, which it knows allowed it to travel 0.24 meters per second. How did the robot search among millions of controllers that it had at hand so that within 4 attempts it found a compensating behavior? Seems almost impossible. Okay. Okay, let's dive into the heart of the algorithm now to see how it performs this efficient search. I'm going to use a couple of cartoons here that I took from the paper to motivate the intuition here. Before we send the robot into the field, we have the simulated undamaged hexapod, and we're going to try out a whole bunch of controllers on that simulated robot and get back one number, how far the robot travels. You remember at the beginning of the course when we talked about evolutionary algorithms, one way to think about evolutionary algorithms is to use this idea of the fitness landscape. If we have a neural network controller that has just one synapse in it, we can set the weight of that synapse to different values. If we treat those different synaptic weights as different points along a horizontal line, we can consider each of those different controllers, each controller with a single differently weighted synapse. We got different controllers, and by changing the weight of that single synapse, we're moving left and right along this horizontal axis. We can ask, what's the fitness of each of those controllers, which is our vertical axis. If we have a controller, like from a Bratenberg vehicle, remember the Bratenberg vehicle had pairs of crossed and uncrossed wires. If you think about a controller for a Bratenberg, that controller has two numbers that describes each controller, the weights of the two synapses. If we set those two synapses as our two horizontal dimensions, then any point in the horizontal plane corresponds to a particular controller. And the height of that point, again, is the fitness of that controller. And we have a fitness landscape in 3 dimensions. The 2 horizontal dimensions correspond to the 2 synaptic weights, and the height corresponds to fitness. If we now have a controller with 3 synaptic weights, we have a 4-dimensional fitness landscape. We have 3 quote-unquote horizontal dimensions, and the 4th dimension is always height. That's what's represented by this tesseract or 4-dimensional cube you see in panel A here. So if we're thinking about all possible controllers that can control this hexapod, I don't know how many synapses are in this neural network. This robot has 18 motors, so it's got 18 motor neurons. It's probably got a bunch of sensors, maybe some hidden neurons. There's probably dozens, if not hundreds, of synapses in the neural network controller for this robot, which means we have dozens or hundreds of horizontal dimensions, and then the last dimension is height. So we have a very high-dimensional search space, the space of all possible controllers over here. In the IT&E algorithm, they're going to compress, or they're going to collapse this high-dimensional space to a much lower dimensional, what they call behavior search space. In order to visualize this algorithm, we're going to assume for the moment that this behavioral search space has just 2 dimensions. What do these 2 dimensions correspond to? They're going to correspond not to synaptic weights, which is the genotype, that's the genetic encoding of the controller. Instead, these 2 dimensions are going to correspond to the phenotype, which is the thing produced by the genetic blueprint, by the genotype. The phenotype here is the way in which the robot moves. The first video I showed you from this project, we were looking at different gaits and how much the fraction of time that a leg spent on the ground. Let's imagine we're going to watch all of the controllers in this high-dimensional space. Well, not all of them, but we're going to play a bunch of controllers on this robot. And for each controller, we're going to measure the fraction of time that the front left foot is on the ground and the fraction of time that the front right foot is on the ground. We're just going to look at the front 2 legs for a moment so that we can think about behavioral space as 2-dimensional. You can now think about each point in this 2-dimensional plane as the result of a given controller. How much the percent of time that controller causes the robot, let me try and rephrase this. We take a controller from this high-dimensional space, we run it on the hexapod, Let's say it's the left leg spends 30% of the time on the ground and the right leg spends 20% of the time on the ground. So we go to 30% on one dimension and 20% on the other. And we color that pixel based on the speed of travel of the robot. So the behavioral search space, like the original search space, the height, which we're going to just represent as color here to keep things flat. The color represents the speed of travel of the robot. We're going to use a heat map or a particular color palette where hotter colors like orange and red correspond to faster moving robots, and yellow and green, the cooler colors, correspond to slower moving robots. Okay. This is our this confidence space. I'm going to talk about this in a moment, but I want to just focus on this part, which is the one that's kind of hardest to wrap your mind around. We're compressing this down to a lower dimensional space. There's a problem, however, whenever you compress a higher dimensional space into a lower dimensional space, which is everything in here is not going to fit into here. Let's imagine we have two controllers, two different controllers, so they represent two different points in this higher dimensional space. We run both of those controllers on the hexapod, and both controllers cause the left leg to spend 30% of the time on the ground and the right leg to spend 20% of the time on the ground. So the results from both controllers, we have two speeds produced by those two different controllers, but we're trying to put the results of those two controllers into the same pixel. The pixel that's located at 0.3, 0.2, 0.3, 0.2 in this lower dimensional space. We can't fit both controllers into that pixel or into that bin. What do? We have to throw one of the controllers away. Can't put both of them in there. We can only put one in. What's the one that we put in there? How do we decide? Any ideas? This lower dimensional behavioral space, this lower dimensional behavior space, this is the set of contingency plans that the robot is going to have in case something goes wrong. As Matt mentions, the intuition here is we want to keep very different controllers, but we also want to make sure we keep the best controllers. So if there are multiple controllers that are vying for the same position in this space, we keep the best one. I mentioned, so we're now actually starting to talk about the evolutionary algorithm. The evolutionary algorithm that was used in this experiment, and that evolutionary algorithm is known as MAP Elites. MAP Elites is actually now a very popular and state-of-the-art evolutionary algorithm because it maintains a population of good solutions, but also diverse solutions. If you think about two different locations in the behavioral space, if those two positions have large distance, that means that they cause the hexapod to move in very different ways. Two pixels that are close to one another in behavioral space cause the robot to move in similar ways. Similarly colored pixels, even if they're far from one another, cause the robot to move about the same speed. Color is the thing we're interested in, the behavior. Differently colored pixels cause the robot to move at very different speeds. So how does MAP Elites work? MAP Elites is actually a relatively simple evolutionary algorithm. We generate a bunch of random controllers from our high dimensional space. We create random neural network controllers, run each of them on the hexapod, figure out where those results should be stored in behavioral space, and drop the fitness values into those pixels. And if there's a collision, we keep the best one. We then randomly grab one of the pixels that's just been filled in. So one of the controllers we just tried. We take that controller, we copy it, we introduce a mutation, we drop it back into the simulated robot. And if the simulated robot moves differently, that means that we move in behavioral space. We take the fitness value and we try and drop the fitness value into that new pixel. If that pixel is unoccupied, no problem. We put that fitness value and that controller into that pixel. We now have a bunch of controllers that are sprinkled throughout this two-dimensional space. We grab another one at random, copy it, mutate it, drop it back into wherever it's supposed to go in the behavioral space. And as we continue, we start to fill up the pixels in this space. And as we keep going, there are more and more collisions because more and more of the pixels are filled with a controller and its corresponding fitness value. If there's a collision, we throw away the controller that produced a slower moving robot. And eventually, we start to get a picture that looks like this. We have peaks of high, fast-moving robots and valleys or troughs, these cool colors that contain controllers with slower moving robots. Make sense? That's the Map Elites algorithm. Pretty simple. Again, you got a few weeks left for those of you that want to try replacing the parallel hill climber with Map Elites. Go for it. Any questions before I move on? Okay, so in this cartoon, this behavioral space is two-dimensional, corresponding to two of the 6 legs. In this experiment, the behavioral space is actually not two-dimensional; it's 6-dimensional because the robot has 6 legs. Any controller that we run on the simulated hexapod, we can measure the fraction of time that each of the 6 legs spends on the ground, which gives us back 6 numbers. We can treat those 6 numbers as a coordinate or a location in 6-dimensional space. The way they actually did this was to create a 6-dimensional space, but that space is discretized into bins. What do I mean by that? Let's imagine we run one controller on the robot, and it causes the left leg to spend 20% of the time on the ground, and what did I say before? The left leg to spend 30% of the time on the ground, and the right leg to spend, I'm going to just write this into chat so I remember. Left leg spends 30% of the time on the ground, right leg spends 20% of the time on the ground. So dimension 1, the left leg, you can see that there's actually 5 bins arrayed along the horizontal axis. Each bin is going to capture controllers. The first bin is going to capture controllers that cause the left leg to spend 0 to 20% of the time on the ground. The second bin is going to capture controllers that cause the left leg to spend 20 to 40% of the time on the ground. The third bin, 40 to 60% of the time on the ground. Fourth bin, 60 to 80%, 80 to 100. So left leg spent 30% of the time on the ground, 0 to 20, 20 to 40. It's going into this second bin. Same thing for the second dimension. The second dimension has 5 bins corresponding to whether the leg spent 0 to 20% of the time on the ground, 20 to 40%, 40 to 60%, 60 to 80%, or 80 to 100% of the time. In this cartoon example here, the right leg spends 20% of the time on the ground. The first bin captures 0 to 20% of the time on the ground. So this controller is going to go into the first bin here and on the horizontal axis, second bin on the horizontal axis. So where the controller is going to go somewhere into this bin. You'll notice that this bin itself is broken into a smaller set of 5 by 5 bins, which correspond to the third and fourth leg. So the same single controller that we're considering, we look at how the fraction of time that the middle left and the middle right leg spent on the ground, and that will allow us to index or determine which of the 25 bins in here, we should be placing that controller. When we find one of those smaller bins, that bin itself is a bin that is composed of 5 by 5 pixels. Which of those 25 pixels is this controller going to attempt to fill? It depends on the fraction of time that the 5th and 6th leg spent on the ground. Make sense? Again, it's a little tricky to try and wrap your mind around thinking about 6 dimensions. This is a way to visualize these 6 dimensions in a 2-dimensional plot. Okay, so once we've located the exact pixel where this controller is supposed to be, we color that pixel based on the speed of travel of the simulated robot. If there's another controller there that causes the robot to move slower, we eject that controller and replace it with this controller. Okay, so here's a picture of what the map actually looks for. This algorithm is called the map elites algorithm. This is what the physical hexapod has when it goes into battle, when it goes into, when it starts to perform behaviors in the real world. You'll notice that some of the pixels are actually white. So the map elites algorithm has already finished running. The map elites algorithm has considered millions and millions of controllers, but not all of those controllers produced fractions of time that the robot is on the ground. You'll notice there's actually more white towards the lower left. Why do you think that's the case? Most of the pixels are filled in. The map elites algorithm found controllers that caused the robot to move in such a way that certain legs spent certain fractions of the time on the ground. Why mostly white pixels? So these are unoccupied pixels in the lower left. What does that mean? The very lowest, the left lowest pixel here at 0.00000, at that particular coordinate in 6-dimensional space, if a controller were to occupy that pixel, what does that controller cause the robot to do? Any ideas? Remember that these 6 coordinates represent the fraction of time that the legs were on the ground when the robot is controlled by that controller. A controller that produces 0.00000 means it's a controller that caused all 6 legs to be off the ground all the time, which is impossible. It's hard to see in this picture. It looks like some of them are filled in here, but I think that's just an artifact of the way this is drawn. So it's very difficult to find a controller that causes most of the legs to spend most of the time off the ground. It's much easier to find controllers that are in the very upper right, which is that most of the legs are spending most of the time on the ground. You'll notice that there are little splashes of red in this picture. These are the most fit controllers in this population, embedded inside this map. These are the ones that cause the robot to move quickly. Blue pixels are those that cause the robot to barely move at all. Okay. Logan says that's not necessarily true. That robot that flipped over seemed to not have any legs on the ground for most of the time. Right. Good point, Logan. It may actually be that the 0.00000 is filled in, and it might be filled in by exactly that controller that flipped over on its back. That's why I think you actually do see some colored pixels in the very lower left. Perverse instantiation makes some of these controllers possible. Good point. Okay, so here we go. So we've got this here. We now deploy the physical robot into its environment, and it's got to pick a controller out of the map to use for control. Which controller does the physical hexapod choose? It chooses the controller that's located in the pixel with the hottest color, which is around here. Let's say the robot takes that controller and runs with that controller, but if the damaged robot is damaged, it's unlikely to move quickly because this controller has a hot pixel because it caused the undamaged hexapod to move quickly. So usually the robot's surprised. It was surprised. It was expecting to move quickly, but it didn't. So it updates the colors of the pixels. You can think about hot colors as hills and cool colors like green as valleys. So the physical robot says, I thought this controller and controllers nearby would work well, but they didn't. So I'm going to cool all of the colors. I'm going to cool the color of the pixel corresponding to the controller I just tried. And I'm also going to cool nearby pixels because nearby pixels contain controllers that cause the robot to move in a similar way. So again, this is an idea that comes from the Transferability project, which is if a controller does badly, similar controllers are also likely to do similarly badly, similarly poorly. Okay. Let's talk about this other two-dimensional space up here. This is known as the confidence space or the confidence level. This space corresponds, each pixel in this space has a corresponding pixel in this space and vice versa. The color of the pixel in the confidence space is how confident the physical robot is that controller will, it's the confidence that the physical robot has on how well these controllers will transfer to reality. This is almost like transferability, or it's actually uncertainty about transferability. So the robot says, these I think are going to perform poorly, and I'm pretty sure about it. You'll notice that the heat of these pixels has increased. Why is its certainty about these pixels, why is its certainty about these higher? Because it obviously has sent one of these controllers to reality. It's maximally certain about the color of this pixel, which is now green, bad, because it was bad when it went to reality. It's a little less certain about ones that are nearby. It says, I think this pixel is light green, but I'm of medium certainty about that. I haven't actually transferred this controller, so I'm not quite sure. The blue that you see everywhere else, this is the robot saying, I have no idea. In simulation, these controllers, and these controllers do well, but I don't really know, I'm not really sure about it. So the robot, it was clear which controller to send first, this one. Now in panel D, the robot has to choose another controller to send to reality. Which one should it send? The way the robot determines this is it multiplies the value of each pixel in the behavior space. It multiplies it with the value of the pixel in confidence space. So we now have a third space which contains the products of each of those multiplications. And the controller that the robot is going to try next is the one that has the highest product. We're looking for a controller that has high heat, that causes the simulated robot to travel quickly, and that has high confidence. The robot is confident that it will also have high heat. It'll cause the physical robot to move quickly if sent to reality. So we've got a bunch of low values here being multiplied by high values over here. And we have high values over here being multiplied by low values over here. It's kind of a toss-up. We have low values in here in the green that's being multiplied by low values up here. Those are definitely not going to be the controllers that we send to reality. In this cartoon example, we're assuming that this is really, really hot over here. So even though the robot is not so certain about these controllers, this controller, it's going to send this controller to reality next. And this controller also didn't transfer well to reality. So the robot increases its confidence about these colors in the confidence space. So every time the robot sends a controller to reality and gets the result back, it is changing the colors of the pixels in behavior space, and it's also changing the colors of the pixels in confidence space, multiplying pairs of pixel values together, getting a space of products, and looking for the highest product. It's looking for the pixel or the controller that is predicted to cause the robot to travel fast, and there is high confidence about that predicted transferal. Make sense? Okay. It turns out by doing that, after 1 transferal, 2 transferal, 3, 4, on the 5th trial, more or less, the physical robot starts moving again. This algorithm, the IT&E, intelligent trial and error, allows the robot to rapidly find within a space of large numbers of controllers those that recover functionality in the damaged robot, even though the physical robot does not know how it's damaged. Okay. Here's a picture of what actually happened. So as the physical robot started acting in its environment, this was the robot's understanding of how all the various controllers would work. The robot started with this controller over here, which is, if we go back over here, this is where the most red was. This was the one most likely to work. You'll notice, actually it's hard to see because of the circle here, but this area became cooler afterwards. This controller did not work. We're not seeing the confidence space in this case. It went over here next, which, as we can see, has high heat over here. That controller also didn't work. So it cooled off this area and increased its certainty about things in this region. It went from here to here, then 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 to here. And you'll notice for this one and for this one, they remained relatively hot areas. So the robot was starting to converge on an understanding that these areas are hot, and the corresponding 6-dimensional confidence space are also relatively hot. The robot says, I got a bunch of controllers over here that are good for the simulated robot, and I'm pretty confident that most of these actually also produce fast movement in my physical form. There's some remaining hot values over here. They're actually hotter than they were before. But the robot hasn't tried out any controllers near here yet, so it's probably not so sure about this region. So this is the robot's understanding before deployment. This is the robot's understanding after deployment. It's got a whole bunch of contingency plans, and if we were to ask the robot, it'd say, these ones, I used to think they were good, but now I think they're not so good. But these regions down here, I originally thought they were good, and I still think they're good. Okay, let's look at some results before we conclude for today. They ran this IT&E algorithm 6 times for 6 different damage scenarios. C1 is actually the undamaged robot. C2, half of one leg breaks off. C3, one leg becomes unpowered. It's just dragging this leg behind it. C4, an entire leg is missing. C5, 2 entire legs are missing. This is a pretty dicey situation. C6, they replace the lower leg with a wooden block. I mentioned before NASA's interested in rovers that are moving through mud or material, and they actually add material or material gloms onto them as they're moving, and the part becomes heavier or bigger. Okay, so let's look at some results here. We have our 6 damage scenarios along the horizontal axis here. The vertical axis represents the walking speed of the physical robot, measured in meters per second. The star in each of these 6 columns corresponds to the walking speed of the robot after this has happened. The first star is high because obviously the robot is undamaged, and in this situation it was able to travel 0.25 meters per second pretty quickly. Right after it lost half of one leg, it dropped to moving 0.03 meters per second, starts moving pretty slowly. And you can see in the other 4 damage cases, the damaged robot immediately is moving pretty slowly. The purple bars that you see here is the average walking speed of the robot in each of these damage scenarios after it's been able to try out a couple of controllers in reality and update its behavior space. And you'll notice that these purple bars are almost back to 0.25 meters per second. It's almost recovered full speed. In the case of C5, it's still not, it only ever recovers on average about 0.16, which is not surprising. The robot's lost 2 total legs. But the fact that the purple bar is significantly above the star tells us that significant speed was recovered from the damaged robot. Okay. This little panel over here, which says alternative descriptor, this represents an alternative way of describing the behavior space. So in the behavior space here, we describe the diversity of controllers by the fraction of time that the legs spent on the ground. We could use other behavioral descriptions. We could use the height of the robot's body as one dimension while the simulated robot is moving. The second dimension could be the orientation of the robot's body after it finishes moving. We could come up with different behavioral descriptors, which would give us a different embedding or a different mapping. They showed that for at least 2 of the different damage scenarios, the undamaged case and this damaged case, with an alternative descriptor, the robot also lost function and was able to significantly recover it with just a few trials. This plot is reporting the same results, but they're showing now, they're showing here in the insets, they're showing the amount of time that the physical robot required to recover. So if we look at C5 here, this significant damage case, the robot's barely moving, and it takes it about an average of 2 minutes to recover on average this amount of speed. So we can now ask the question, how much function does the damaged robot recover? And how long does it take it to do so? And on average, it takes about a minute, maybe no more than 2 minutes to recover that speed. That's pretty good if the robot is in a dangerous situation. We've got 3 minutes left, so I just want to finish up this lecture by pointing out that the authors also showed that the same approach works for other robots. In this case, not a hexapetal robot, but this was a robot arm that was supposed to take orange ping pong balls and drop them into a tin. They looked at 3 different injuries to the robot arm. One of the joints can become stuck at 45 degrees. They looked at motors in which the joint had a permanent offset. So instead of rotating through this angle, the robot would instead always rotate through this angle. That can happen if something gets bent, if the robot becomes physically bent. They looked at combinations of damages. So they looked at 3 different damage scenarios, C1, C2, and C3. And they show that this robot can recover, the robot arm can recover from damages and return to dropping ping pong balls correctly in the tin after about 15 seconds. Okay, there's a video of the robot arm. You can watch that online at your leisure. That concludes our discussion of the robots that can adapt like animals paper, or the IT&E algorithm. It also concludes our discussion of crossing the reality gap. We will start on Tuesday by talking about the Twitch Plays Robotics project, which is an attempt to scale up evolutionary robotics so we can have hundreds or thousands of people collectively guiding the evolution of hundreds or thousands of robots. Good luck with your final project. You have a quiz due tonight, and come see Amanda and I during office hours. Otherwise, I will see you all back here next Tuesday morning. Thanks very much, everyone. Have a good day. Bye-bye.